Okay, welcome everyone. So we are just about ready to wrap up our introduction to determinants. And so let's recall that if A is a square n by n matrix, then we can define the determinant of this matrix with the following sum, okay, where we take, say we go across the top row, we take the A1 entry times the determinant of sub matrix A11 minus A12 times the determinant of submatrix A12 all the way out to the nth column where we're going to take the A1n entry. Depending on whether we add or subtract that is going to depend on whether 1 plus n is even or odd. And then we multiply by the determinant of the submatrix A1n. And then remember, depending on the size of these matrices, calculating the determinant of each of these submatrices is going to involve a whole bunch of calculations in itself. So let's kind of talk about how different ways that we could write out this formula. And so it's going to be useful to shorthand some of this. So the stuff in the term where we have the power and we have the determinant of the submatrix. So now if I attach the sign to the value of the determinant, we call this the cofactor. So this minus 1 to the ij power times the determinant of submatrix aij, that's called the ij cofactor of the matrix. And we denote these cofactors with a cij. And by introducing cofactors and using this notation, we can cut down on some of the notation in this sum. And now we can write out the sum more simply by saying the determinant of A is equal to the sum as column j goes from 1 up to n of A1j times cofactor 1j. And so if we expand that sum out, we would start with A11 times cofactor 11 plus A12 times cofactor 12 and so on. So this just gives us a way of kind of sucking up the minus 1 to the I plus j in with the determinant. So it's a little bit less notationally, but of course we need to know what these cofactors are. So this formula that we've just written out going across the top row of the matrix, we would call this the cofactor expansion across the first row. And we can do this across other rows as well. So I can calculate the determinant of matrix A by using a cofactor expansion across any row. So what was special in this first formula is that we set I equal to 1. So all of the i's in this case were set equal to 1. If I want to do this more generally across the ith row, then I'm going to take the sum as j is going from 1 up to n of aij times cij. So that would look like ai1 times ci1 plus ai2 times ci2 all the way out to ain times cin. So we can do this for any row. And if you have a row that has a bunch of zeros, that's probably the row that you want to do this expansion across. Okay, so we have been working with determinants of any square n by n matrix A. And so far we've shown that we can calculate the determinant of A using a cofactor expansion across any of the rows that we want. And if we're strategic, we might pick a row that has a lot of zero entries in it. What this theorem is stating, and I'm not going to prove this theorem in general, but on the next slide, we'll kind of verify that it's true, is that not only can I choose to go across any row of the matrix, I could choose to do a cofactor expansion down any column of the matrix as well. So what that would look like formula-wise is I can calculate the determinant of matrix A using a cofactor expansion down the jth column of matrix A. So for example, I have some matrix A. Here's the jth column of that matrix. So I pick the first entry in that column, A1j, and depending on whether 1 plus j is even or odd, right, we have a plus or minus sign, and then we multiply by the determinant of submatrix A1j. So I would eliminate all of these entries all of these entries, and we have an n minus 1 by n minus 1 matrix that we would calculate the determinant of. And so that negative sign raised to the power of I plus j times the determinant of the submatrix, we call that the cofactor. So I can write this cofactor expansion down a column as saying A1j times cofactor 1j plus A2j times cofactor 2j, and so on. So in this example, when we're doing a cofactor expansion down a column, then we fix the value j. We fix the column, and we are going to look at all of the different products of A1j, so that would be the first row times cofactor 1j. And then we go down to the next row and do the same thing, and then the next row until we reach the last row. Okay, so to summarize, to calculate the determinant of a square n by n matrix A, we can use a cofactor expansion down any row, or we can go across any column, and we should be strategic as far as which row or column we pick to help minimize the amount of calculations. So let's take a look at one last example on the last slide.